Now let's take a closer look at constant acceleration over a given displacement. We know what to do when it's constant acceleration for a given time. We use the standard kinematics expressions that come straight from calculus. V final equals V initial plus acceleration times time. That's one. And then position final equals position initial plus V initial times time plus 1/2 AT squared. That's the other one. And keep in mind, these mean delta T equals the final time minus the initial time, as always. But often when we write these, we say the initial time is 0 and the final time is just T. We're thinking about the time from the origin up to some time T. So that's why we don't see delta T's. Anyway, this is what we use to solve a lot of problems. And if you think back to the ping pong ball drop, that was an acceleration over a certain displacement, and we solved it by combining these. But it might be useful to just combine them ahead of time and come up with one expression. And that's what we're going to do and see what we get. So what we're going to do is solve this one for T and plug into this one. All you got to do. So let's solve this for T. That is V final minus V initial over A. So there's T, and now let's plug it in here. I'm going to go ahead and write the displacement by bringing the initial position to the other side. So there's the displacement, and that is the initial velocity times the final minus the initial velocity over A, VIT, plus 1/2 A, and then this expression squared. Final velocity minus initial velocity over A quantity squared. So you could say we're done. Just memorize this and use that. But of course, it's better if we can simplify it to something short and easy to remember, because kind of having another one at your fingertips is sort of the whole point of coming up with this equation. So let's simplify. Let's multiply by 2A. Each side by 2A. On this side, we're going to get 2A times the displacement. And then here, let's look term by term. That A, when we multiply by 2A, it's going to cancel there. So you're going to get 2 VI, V final minus V initial. And then this term, the 2 is going to cancel the half. This A and this A will make A squared, but there's A squared in the bottom. So those are all going to cancel. That's why I chose 2A. And all you're left with is V final minus V initial squared. The change in velocity squared. And you look at that and say, okay, well, that's not really fun to memorize either, is it? So what we're going to do is write this as 2A. I'm going to go ahead and write it as delta X, just to get us there. 2A delta X. And then here, notice you can factor the change in velocity. You can factor out VF minus VI. Both terms in this sum have that in them, which will leave you with what's left here, 2 VI, okay, plus what's left here is another VF minus VI. And you can balance out all your parentheses, but you don't really need to. Really. These are all just 3 summed terms. So then we can simplify this. The 2 VI minus the VI gives us 2A displacement is VF minus VI times what's left, VI plus VF, or we could write it VF plus VI. All right. So we're down to just 2A displacement delta X equals VF plus VI times VF minus VI. And you may remember that. Sounds familiar from algebra. That's the equal to the difference of 2 squares. A plus B times A minus B is equal to A squared minus B squared. Because if you FOIL it, the cross terms cancel. So we could also write this 2A delta X equals V final squared minus V initial squared. And if we rearrange it, now we're to that famous other kinematics equation that you may have memorized in your youth. If we say V final squared, bring this to the other side, equals V initial squared plus 2A delta x. I learned to call that d for displacement, but here we will stick with delta x. And now we have it down to something that's short and useful and easy to memorize. But I just want you to recall or to know this is not some fundamentally new kinematics equation with new information. It's really just a combination of these two. And this would have helped us out quite a bit to do the ping pong ball drop. Each one would have been one step.